All right, guys, welcome to our Unit 2 test study guide. So let's go ahead and begin. So this problem here, we have to, a big part of this test, you guys, is recognizing what integrations rules to use, when to use them, and how to use them. Okay, so when I look at this one, this is a power rule problem because I recognize that I could rewrite each of these problems as powers. So that's the first thing we'll do there is rewrite both of those as powers. The next thing we do when you do the power rule is you add 1 to the power. Now when you add 1 to a fraction, that's like adding the top and bottom together. So you get 6, and then you keep the denominator the same. And what we're going to do now is usually we would divide by that new power, but in this case, since it's a fraction, we're actually going to multiply by the reciprocal. Okay, so that's the integration of that first piece. Now we'll do the next piece. If you add 1 to this, you get -1, and then you also want to divide by that value. And let's not forget our plus c. So now we get to fix things up a little bit. So the 5's here cancel, and 6 goes into 12 twice. So I'm left with -2x to the 6/5 power. And then these two negatives are going to become a positive. This 3 is going to stay in the numerator, while this x to the -1 goes down to the bottom as a +1. And there's our final answer there for number 1. All right, let's go ahead. I'm only gonna do on the video here the ones that I'm requiring you guys to do. There are other ones and an answer key as well provided for those if you want extra practice. Like I'm not gonna do number 2 just because it's not required. I'm also gonna be skipping number 3, but I will go ahead and move on to number 4. So let's take a look at number 4. This is a U sub problem. How do I know that? Because I see an inside function as well as its derivative on the outside. The derivative of 3x squared is 6x. Now when I say I see its derivative, that doesn't mean it has to be exactly the same. Like maybe the derivative could be 4x. All that matters is that whatever's the derivative of the inside will cancel the x out here. Okay? There is one exception to that, which I think we'll look at in just a moment. But for now, that's usually how you can identify U substitution. So U is equal to 3x squared plus 2. Which means that du dx is equal to 6x, which means that du over 6x is equal to dx. Next, we're going to go and do the U substitution. We're going to replace that whole thing with u. And we're going to replace that with du over 6x. And notice that those go away, leaving me with a little bit of a cleaner looking expression there. Doing our integration, it's a power rule, so I would just add 1 to the power and divide by that value and put plus c. Finally, we replace the u with what we know u to be, which is 3x squared plus 2. And there we have it. So that's the end of that one. That's what I would call a basic U sub problem. Let's go ahead and take a look at number 5. These problems they're kind of ugly. So it's another U sub problem though. In this case, the U is the stuff inside of here. So my U is 4 plus ln, and I really don't like how they write that because it looks like it's ln minus 6 and it's not. It's ln of -x. Or I said minus 6, I meant minus x. But anyway. So I like to use parentheses for the part that comes after ln. So just be aware it will be like that on your test also, and I prefer to use parentheses. So I think it's nice, but you don't. So long as you know it's not minus x, it's ln of -x. You're good. All right, let's go ahead and find our derivative. So first of all, if I take the derivative of 4, that's just going to go away. So the 4 is gone when you take the derivative, right? And then for ln, the derivative of ln is 1 over whatever you're taking ln of, in this case -x, times the derivative of the inside, which is -1. These negatives cancel, and I'm left with 1 over x. Now, anytime you're doing u substitution and your u has an ln in it, so you get this expression. Getting the dx by itself is going to be a little different than usual. So first of all, of course, you're still going to multiply both sides by dx. Oops, little issue there. Right? But now I want to get this to the other side. So the way you do that is multiply both sides by x. And so what we end up with is x du is equal to dx. So let's go ahead and do our u sub and see if we can make this ugly expression here look a little better. So we have 4, and everything in parentheses there is our u. And then we're going to replace the dx with what it equals. It equals x du. And in this case, these x's go away. So in the end, this simplifies into something a little bit easier on the eyes, which is that. And now we can go ahead and do our power rule where we add 1 to the power. And remember, when it's a fraction, adding 1 to that is like adding the top number and the bottom number together. So you get 4, but you keep the denominator the same. And you don't want to forget your c. Also, we need to divide by this number, but since it's a fraction, we talked about how instead of dividing by a fraction, it's easier to multiply by its reciprocal. And so the 4's cancel, and now I have this. The final thing I need to do is to replace the u with what I know u to be. And u is 4 plus ln of negative x. At this point, I won't put the parentheses on just because that's what the answer would look like on the multiple choice, but just remember it's technically ln of negative x, not ln minus x. All right, and just so you know, ln minus x doesn't make sense anyway because ln's not a number, it's a function. All right, next problem, number 6. U sub again. Here's my u, my derivative. When you take the derivative of an e function, you get the e function all over again, but you do need to multiply it by the derivative of the exponent, which is 5. And the 2 just goes away, so we can ignore the 2. Getting the dx by itself, we have 5e to the 5x. And then doing our u substitution, I'll replace that with u. And I'm going to replace that with du over 5e to the 5x. These go away. 5 goes into 15 3 times, leaving me with 3u to the 1/2 du. I'm going to add 1 to our power to integrate. Multiply by the reciprocal. These cancel, and so I'm left with 2u to the 3 over 2 plus c, and the u is e to the 5x minus 2. Final answer. All right, let's go ahead and move on to number 7. All right, now this is a weird situation, and here's why. Because I told you guys that the way to recognize u sub is you see an inside function, so that's good. But then you see the derivative on the outside. Well, the derivative of this is just 3, and there's no 3 on the outside, but I do have this extra x. This is a rare occasion, but it does happen sometimes where we're still going to do u sub even though the derivative is not on the outside. And that causes us to have an extra x left over, and we have to go back and replace it. So that does happen sometimes. It's not very common, but we'll include it here. So we have u equals 3x minus 4. And the derivative of u with respect to x is 3. And then getting dx by itself, we have that. Doing our u substitution, we get 3x minus 4. Oops, I'm not doing the u sub, am I? Back up a little bit. We're going to replace 3x minus 4 with u. That x is there, and now I'm going to replace dx with du over 3. Okay. So at this point, what I'm going to do is I'm going to rewrite the expression a little bit. When you have an x left over, we want to put everything together that's not the x or the du. We'll leave the x and the du right where they are. But I want to put that u to the negative 4 and that 3 together. And if I do that, it'll look like this. Okay. Now, the next thing I want to do is I want to go back to my u equation, and I'm going to solve for x. I'm going to get x by itself. So let me show you what I mean by that. We're going to add 4 on both sides. And then we're going to divide everything by 3. Now that I know that x is equal to this, I can replace x with that. So if I do that, I get the following. And now we can go ahead and distribute. Make a little bit of writing space for myself here. But if I distribute this fraction into these ones, we do top times top and bottom times bottom. So this is u to the first power. So if I do u to the negative 4 times u to the positive 1, you just add their exponents together. And what you're going to get as a result is u to the negative 3. And then for the bottoms, 3 times 3 is 9. And then we distribute it over here too. So we get, in that case, 4u to the negative 4 over 9. And after that, we're ready to integrate like we normally would. So you're going to add 1 to the power, which makes it become negative 2. And you divide by that number. Now, I've already got a number in the bottom. No big deal. I'll just put times and then put the negative 2 down there also. Next, 4. I'm going to add 1 to the power, and I'm going to get negative 3. Keep the 9 down there, and we're also going to put the negative 3 down there. And we want our plus c. Now we can simplify this a little bit. So right now I've got u to the negative 2 over 18, and it's a negative 18, but I'm just going to put the negative in front of the whole fraction there like that. Same thing here. We have 4u to the negative 3. Right, I don't know where, I had to get up, I had to pause my recording for a second, so I don't remember where I left off, but anyway, we were in the process of multiplying these together, so we get 27, but it is negative 27, which once again, that's just going to make the whole fraction there negative. All right, there's that. And then finally, well, not finally, 2 more things. We need to take those u values and put them in the bottom. Now it's possible they'll leave it on the top. I'm kind of curious how they're going to write it. Let me see, because I want to write it the way it'll look on your test. They do move it to the bottom. Okay, so we'll do that. All right, so first thing then I'll do is I'll take these u values, since they have negative powers on them, and we're going to move those to the bottom. So we have negative 1 over 18 u squared, and then 4 over 27 u to the third. And then finally we go ahead and put the u back in, which is 3x minus 4. And there's our final answer for those. Those ones are kind of a lot of work, so sorry, sometimes those things happen. Let's go ahead and take a look at our next one, number 8. It's another u sub problem. This one's kind of unique though. The u is 3x cubed minus 2. It's there twice, and that's going to come into play a little bit later, but for now, let's go ahead and just find our derivative. That derivative is 9x squared, which means that du over 9x squared is equal to my dx. And then finally, we can do our u sub. So we have negative 45x squared, cosecant, and then there's my u, the 3x cubed minus 2. And then cotangent, and since the 3x cubed minus 2 is there again, I'm going to put u in there again. And we also replace the dx with that. And the x squareds are going to cancel out. and 9 goes into 45 5 times. So there's still a negative 5 in the front there. So let's go ahead and pull that out to the front. There is an integral for this, and that integral is negative cosecant u. Don't forget your plus c. Now notice I put that in brackets because if you don't have the brackets there, it looks like this. And that is technically written wrong because that looks like you're saying negative 5 minus cosecant, and we're not. It's really negative 5 times negative cosecant. So you could put a dot or you could use brackets. It doesn't matter. Just make sure that somehow you indicate that we are multiplying. So we have negative 5 times negative 1, if you want to think of it like that, and it becomes positive 5. And then finally we'll go ahead and put the u back in, which is 3x cubed minus 2. And we have our final answer there. All right, let's go ahead and take a look at number 10 as our next problem. I'm not going to do 9. I'll leave that as an extra problem for practice if you want to. Number 10 is extremely confusing looking. There's just a bunch of trig things everywhere. But the good news is it's kind of easy to see our u, so let's just start there. Now, this is a chain rule. You don't want to miss that. First of all, the derivative of cosecant is negative cosecant cotangent, and you leave the inside alone. But we do need to multiply it by the derivative of the inside. The derivative of the inside is 5, so we need to multiply this by 5. Now just to save some space here, if I multiply this thing by 5, all that's going to end up doing is putting a negative 5 in the front, because the negative makes the 5 negative, and then there would be a 5 in the front. So I think just to save myself some time, I will go ahead and just squish that in there now. Also save myself some space. So we have the derivative of the outside times the derivative of the inside. Next we want to get dx by itself, so that entire thing is going to go underneath the du. All right. Now we're ready to go ahead and do our u substitution here. So I've got negative 15 cosecant, and then that 5x that comes after that, I like to put it in parentheses, and I wish they would, but they don't. And then we have cotangent to 5x. And then we have cosine. And then that's where our u comes into play. Then my dx I'm going to replace with this whole thing here. I'm actually running out of space, so just a second here. So we have du over, and then that big long thing we had earlier, which was negative 5 cosecant of 5x cotangent of 5x. And here's where all the good stuff happens. Cosecant cotangent 5x cancels out completely. So this whole thing just goes away. Also, this negative 5 goes into this negative 15 3 times. So I'll just put that constant out towards the front. And all I'm left with on the inside now is a cosine of u du. Well, the integral of cosine is simply sine. And the last thing I need to do is just put the u back in, and this was my u to begin with, so it's cosecant of 5x. So there's our final answer on that one. Let's go ahead and move on to number 11. All right, so what kind of integral rule is this? Well, we have a square root with some perfect squares in there. Nothing on the top other than a 1, so that's usually an indicator that we're going to have some kind of an arc trig function, and in fact this is an arc secant function. So when it comes to arcsecants, the way it works is you do 1 over a, and a is the square root of that number. Then you write arcsecant. And then we have the absolute value of the square root of that number all over the a again. And you don't want to forget your c. And that's it. That one's all done. That's a nice little breath of fresh air after all those other hard ones we had. All right, now this one almost looks like an arcsecant again. It's got some problems though. We don't have just a number on the top. We have a variable. Also, it's not a square, it's a fourth power, but we can easily fix that by making a few alterations. I'm going to rewrite that as something being squared instead. Okay, so what to the second power would give me 4x to the fourth? Well, that would be 2x squared. Once you've got that, we're going to call that a u, and we're going to do the derivative of u with respect to x, which is 4x, and then getting the dx by itself, we have du over 4x. So let's go ahead and do our u substitution here. All right, 4x's go away. And I forgot something. Whenever we're going for an arcsecant, the u is in two places. Here's 2x squared, that's u, right? So I should have put a u here also. So let's take care of that. And now it looks more like a traditional arcsecant expression. And now we can go ahead and do the same rule we did in the last one. So it's going to be 1 over a, which is the square root of that number, arcsecant, and then absolute value of the square root of this over the a again. Don't forget your plus c. And then finally we plug the u back in. Now technically this thing here can be simplified a little bit. As you guys might recall, if it's a square and this is a positive, then this is always positive anyway, so the absolute value doesn't really make a difference. I'm kind of curious how the answer key is going to look here, because sometimes this software simplifies these things and sometimes it doesn't. So I just kind of want you guys to see what to expect for your test. Let's go ahead and push answer here. So they decided to leave the absolute value bars on there, which is fine. Now technically though, we could erase this, and now that those are gone, we can reduce the 2's away, and we could actually just write this instead. So I have seen this software do this sometimes, so it's funny how it just doesn't make up its mind. So just make sure you know both so you can spot them both. Let's go ahead and move on to number 13. Okay, so for number 13, when I see a problem like this, two possibilities come into my mind. U substitution or arctangent. Now, if it's U substitution, what I mean by that is just make the whole bottom your U. I know that's not going to work. And the only reason I know that's going to work now is because that's only going to work to make the whole bottom your U if the derivative, which makes this a power of 3, is on the top. And we don't have a power of 3 on the top. So unless the power on the top is 1 less than the power on the bottom, we're not going to go that route. So that means that we're looking at some kind of an arctangent situation here. So, but arctangent shouldn't have an x on the top, and it also shouldn't have anything except a 1 on the top. And also, for arctangent, these both need to be perfect square roots, and actually neither 2 nor 8 are perfect square roots. And that's kind of an indicator, okay, it's an arctangent, but we need to doctor it up a little bit. So I'm going to start by taking the 6 out of the top. And what can we divide out of the bottom? Well, we could divide a 2 out of the bottom. So if I do that, I'm going to be left with this. All right, and this simplifies into 3, so I'm just going to write that as a 3. Now we're almost there, but it's still not quite ready yet to be treated like an arctangent. And that's because, first of all, there shouldn't be an x in the top, and also it should be a square on the bottom, not a fourth power. But at that point, we're going to solve it the way we did on the last problem like that. I think it was number, I can't remember now, but anyway, we're going to rewrite this as a square. So what to the second power is x to the fourth? That would be x squared. Now this is ready for u substitution because now notice that this power, which is 1 less than this power. Now I'm ready for some u sub, but only that piece is going to be my u. So my u is x squared. The derivative of u with respect to x is 2x. And getting the dx by itself, we have that. All right, so doing our u sub then, we have x on the top, 4 on the bottom, plus u squared du over 2x. All right, so the x's are going to go away, and this 2 I can take out and move outside, and it's going to go on the bottom. Why does it go on the bottom? Because it was in the bottom in here, so you just keep it where it is, basically. So now I'm looking at this, 3 over 2 integral 1 over 4 plus u squared du. Now it's arctangent ready. I've got a 1 in the top, I've got 2 squares in the bottom, and we're ready to go. So here we go, 3 over 2. And for arctangent, we do 1 over a, and a is the square root of that number. And then square root of this number over the square root of that number, plus c. And we do need to multiply straight across here to get 3 over 4. And we also need to replace our u with what we had earlier. U was x squared. And there you have it. So that'll be our final answer there. Go ahead and take a look at our next one, number 14. Now in this case, this is not an arctangent. It's a u sub only, where you make the entire bottom your u. Now why is that? Well, because this power in the top is 1 less than the power in the bottom, so that's your indicator there that that's the strategy we're going to go with. So taking the derivative of that, we get 10x to the fourth. And then getting the dx by itself, we have that. Top is 40x to the fourth. The bottom is u. And dx gets replaced with 10x to the fourth. So the x to the fourths go away. And 10 goes into 40 4 times. And I'm just going to move the 4 out to the front, and now I'm left with 1 over u du. Notice it's 1 over u, it's not just u, because that u's in the denominator, right? So it's a denominator number. There's nothing left in the top, though, so we usually just put a 1 as a placeholder there. And we've been having trouble recognizing this, but hopefully you guys have gotten past that, and you now recognize, oh, that's an ln. And we're ready to go ahead and just replace the u with what it equals. And there's our final answer. All right, let's move on to number 15. All right, so now this is also a u sub problem where the bottom equals a u, but the little rule I gave you doesn't work because we're not dealing with power functions here, we're dealing with trig functions. But think about it. If I make this my u, do you see the derivative of that in the top somewhere? I do. The derivative of sine is cosine. And so if I do make this my u, and I find the derivative of it, it's going to cancel that thing out on the top. So let's find our derivative. It's cosine of 3x. But don't forget to multiply it by the derivative of the inside, which is 3. So getting the dx by itself, we have the following. And then doing our u sub, we have negative 15 cosine of 3x over u, and we'll replace the dx with du over 3 cosine of 3x. So these guys go away. 3 goes into 15 5 times. So I have a 5 and a negative that I'm going to take out as negative 5 there in the front. I'm left with nothing on the top, but I do put a 1 as a placeholder because that u is in the denominator. And once again, we've got an ln for our integral. U is this, so I'll just go ahead and plug that back in, and that'll end it. Let's go ahead and take a look at number 17. I'm going to skip 16 for now, but if you're looking for a little hint, that's your u, so just do u substitution and you'll be on your way. But let's go ahead and take a look at 17. So we want to find the general solution of this. So the step 1 is to separate your variables. So I'm going to move the dx to this side. And you'll notice that there's no y variables on the right side. So what I really have then is I've just got a dy, but I'll put a 1 in the front just so it looks normal. All right. Then we're going to integrate both sides. The integral of 1 dy is just going to be y. This other side, I need to start by rewriting it before I take the integral. And the integral of that, using the power rules that we know of, is to add 1, so we get negative 2, and then we divide by that value. Don't forget your plus c. The next thing we're going to do is we're going to move that x squared to the bottom, and that'll leave me with that. This negative I'm just going to put in front of the whole fraction there. And then we have plus c. And since I want a general solution, that means I don't need to find the c value, and we're done with that one. We'll move on to number 18. Now this one's asking for a particular solution. So once again, we're going to start by separating our variables. I have dy, and I'm going to move dx to the other side. You'll notice that there's no y's to move over to this side, so we'll leave that alone. But just as a placeholder, I'll put a 1 there, and we're ready to integrate. The integral of 1 dy is y. The integral of 2x is x squared. The integral of negative 3 is negative 3x. Well, let's not forget our plus c. The next thing I need to do is plug in my initial conditions so that I can find the c value. This is my x and this is my y, so we'll plug those numbers in. Negative 1 squared is 1. Negative 3 times negative 1 is positive 3. And solving for c, I end up getting negative 3. So my final answer is going to be the general solution, which I found a few steps back, but now replacing the c with negative 3, and we're good to go. You'll notice that the last two I just did are a lot easier than the ones that we were working on in class. If I do include these on your test, the multiple choice test, it'll be like these. The ones that are free response will be more like the ones that we practiced in class. And those will be a little bit more challenging. But I just might include this or I might not on the test. We'll see. But let's go ahead and move on to 20. All right, so now we're entering the world of definite integrals. So this is where we're going to apply the fundamental theorem of calculus. So here we go. So the first thing you do with these types of problems is you integrate. That's a simple little arc sine function there. Take the square root of that and put it over the square root of that. And since it's over 1, we really don't need the 1 on the bottom, but I'll just leave it for now. There's my integral, so now I'm going to go ahead and put these numbers in here. Using our fundamental theorem of calculus, then it becomes this. So arc sine of radical 3 over 2. So you would find where the y value on your unit circle is equal to radical 3 over 2. And it happens at two places. One of those places is pi over 3, and that's the answer. The other one we don't use because with arc functions, we only use the right side of our circle. And next we want to find out where does the y value equal radical 2 over 2. That's at pi over 4. And once again, there's another value where that happens, but we only use the right side. So we have that. Next you want to get a common denominator, which is 12. So I'll multiply this one by 4 on the top and bottom, and this one by 3 on the top and bottom. So now I've got 4 pi over 12 minus 3 pi over 12, which is pi over 12. Let's do another definite integral. So for this one, you could do u substitution where this is your u if you wanted to, and it will work perfectly fine. But I gave you guys a shortcut, and the shortcut will also work. Anytime you have an e to the power of ax plus b and you're integrating it, the answer is always going to be 1 over this number in front of the x, and then the rest of it just stays exactly the same. Okay? Now for r's, I do happen to have an extra little -2 there, which I'll pull out to the front really quick. But other than that, we can go ahead and apply this rule. The number in front of the x is like a 1. So I have -2, so we'll leave that there. And I'm going to have 1 over that number, and then e to the x minus 3, 0, 3. Now I can simplify this. If I multiply this -2 in there, it basically just comes out to be -2 e to the x minus 3. And we're ready to go ahead and plug the numbers in. All right, so there's that. So then applying the fundamental theorem of calculus, we have -2 e to the 3 minus 3 minus -2 e to the 0 minus 3. And so this is just 0, and e to the 0 is just 1. So 2 times 1 is -2, so we're just left with that. This guy here, we have -2 times e to the -3, which is -2 over e cubed. And then these two can become positive, so now I've got 2 over e cubed. Now in this case, we can go farther by getting a common denominator. It's a weird denominator, but the denominator is e cubed, so I'm just going to put an e cubed down here. And whatever you do to the bottom, you got to do the top, so I'll put that up there. And so that gives me -2 e cubed plus 2 over e cubed. And it's not uncommon for them to put the -1 second, so it might be written like this as well. But there's our final answer. Let's see how they wrote it here. Oh, they just left the -1 in the front, but oh well, it's good enough. All right, let's move on to the next one. Okay, let's go ahead and move on to this guy. Sometimes with these ones, it can get a little bit fraction-y. So let's see how this one does. So first of all, we integrate. Next, we go ahead and do our fundamental theorem. Now, when you do this a while back, when you have a lot of fractions everywhere, remember how I recommended to you guys to start off these problems, because this will help you avoid errors with negatives. You also want to write neatly. These problems can be a little bit frustrating because you spend a lot of time on them and you find out, oh, I made a little error somewhere along the way. And then if you're not neat in showing your steps, oops, I just made an error there, but I caught it. It's supposed to be a 1. If you're not showing your steps and being careful, it's easy to make a boo-boo and not be able to find it and have to start all over. So there's that. So cubing -1 is -1, but there's a negative in the front, so it becomes a +1 third. Squaring a -1 is a positive 1, but it has a minus in front of it. And then 5 times -1 is -5, so that becomes -5. This is going to be a pretty hefty number. -4 to the third power is -64, but there is a negative in the front, so it becomes a positive 64. -4 squared is 16, but there is that minus in the front still, and then 5 times -4 is -20. So after you simplify inside those parentheses, I mean, you could actually simplify more inside there, like you can combine these together, and we can combine those together. So let's do that. So now I've got 1/3 minus 6 minus 64 thirds minus 36. But at some point you're going to have to distribute this negative into the second set, and once you do that you can get rid of your brackets and stuff. And that causes both the signs in the second set to switch. Now at this point I'm going to combine everything that's already matching, like this can be combined with this to make 30. And then this can be combined with this to make -63. Now sometimes you get lucky, like I'm going to get lucky here. These are 3 divides into 63 evenly. But if not, you do need to get a common denominator. But for me, it turns out that 3 goes into 63 -21 times. And then we're left with 9 as a final answer. Okay, so it's all about taking your time, being neat, showing your work, having that setup I shared with you, and you'll be good to go. All right, let's go ahead and do some of these. I'm going to skip number 23, and I'm going to do number 24. I'm just going to do the even slope field problems, multiple choice ones. You'll notice that for this one, the rows are the same, and that means that x has no effect on the derivative or the slope, and so therefore there's no x in the equation. So that means this doesn't count. We can't use that one, but it could be any of the other ones. Now, as you guys can see, though, the columns are not the same, so y does affect the slope, and therefore there does need to be a y. So it can't be d, because d doesn't have any y's in it. So it's either between B or D. So after you look at your rows and columns, a good one to look at after that is your zero slopes. So I don't see any zero slopes on here at all, actually. It's possible that they're here, but I don't think so. But we could try it. So let's try plugging in this point. At that point, we have 2, 0. So I would plug 0 in for y. And that would just give me 0. Here, if I plug 0 in for y, I get undefined. So I still don't really know, though, because is there a flat line here and you can't see it because it's on top of the black line? Or is it really supposed to be vertical, but they just decided not to draw a slope whenever it's vertical? Because sometimes they do that because it's undefined, so they won't even put anything there. So that wasn't very helpful. But you do usually want to look at your zero slopes after you've done your rows and columns. So after that, the next thing that you can do is you can kind of look to see where the positive slopes and negative slopes are. Unfortunately, I don't think that's going to help us much either here, because I think they're going to match, because they both are negative and a y. So let's try to approach this a little bit differently. Let's go ahead and try plugging in just a random point. So I'll do this one up here. That's 2, 2. So if I plug that in, I get -2 for this one, but -1/2. So what do you guys think? Do you think that looks like a -2 slope or a -1/2 slope? Well, to me, that looks like flatter than a -2. So I'm thinking we're going to be going with this option here. This one was a little bit difficult because, unfortunately, it was pretty ambiguous. But the point is that you guys want to be looking at the rows and columns. You want to be looking at the zero slopes. And then after that, compare positives and negatives. Let's see what the answer is. It was C. So, but that one was pretty tough, actually. It's pretty ambiguous. Let's go ahead and take a look at number 26 here. So I don't see any parallels in the row, and I don't see any parallels in the column. And that means that our equation has to have an x and a y. So we can rule this out. Next, we want to look for our zero slopes. Now I can see it this time. I do see zero slopes here. So it looks like anytime x is 0, we have a flat slope. But also here, anytime y is 0, we have a slope. So for these points, y equals 0, and for these points, x equals 0. And for both of them, we get 0. Now, for this one here, if y is equal to 0, then that would be undefined. So for all these points, we should have a vertical tangent line, but we don't. So that can't be it. And for these ones, if x is equal to 0, that would be undefined. So anywhere down here, we would have to have vertical lines, but we don't. So that's not it. But here would be our answer, because whether x is 0 or y is 0 on these axes, that'll make the slope 0. So that one was pretty easy to find. So there's that one. Let's go ahead and move on to number 28. So now we're going to look at special integration techniques here. All right. So this is a splitting the numerator. I don't think u sub is going to work up front right away because this plus 3 is in the way. But we are going to go ahead and split the numerator. And I think after we split the numerator, then u substitution can be used. But until we actually split them up, u sub won't work well. All right, so we want to integrate these separately. So I'm going to actually just make them separate integrals. So let's start off with this side here. I'm going to make my u x squared plus 4. My du dx is 2x. So doing my u sub, I get x over u, du over 2x. And then this x cancels this x, and the 2 can come out to the front as a half because it's in the denominator. And so, continuing that over here, then I have 1 over 2 integral of 1 over u du. And that's an ln, so I can just do ln. I'm not going to put my plus c yet. I'll tell you why soon. And then plugging the u back in, we get x squared plus 4. The reason I'm not doing the c is because we still have to do this one, and they're just going to share a c. So I'll just do the c at the end. All right. So for this one, u substitution won't work. But if I take this 3 and move it out to the front, it does make a pretty sweet little arctangent problem. So with arctangent, I really don't need to have any other work to show. I can just kind of skip right down to it. It's going to be 3, and then arctangent. Oh, sorry. I'm going to put a fraction in the front, actually. 1 over a. A is the square root of that number. Arctangent of square root of that over a again. And I can't fit my c in there, but I will at the end. So let's go ahead and put all this together. Then we have half ln of absolute value of x squared plus 4 plus 3 over 2 arctangent of x over 2 plus c. And there's my final answer for that one. So it's a splitting the numerator. And once you split the numerator, it's like you really just have 2 separate problems that you're doing. Let's go ahead and move on to number 29. On number 29, we have a trinomial in the denominator. When you have that, it's going to be a completing the square type of problem. So for completing the square, what we're going to do is we're going to take this denominator, and I'm going to create a new number between the second and the last. I'm going to create a new number. After that, I'm going to also subtract that same value over there. So the new number I'm going to create is found by taking half of that middle number there, which is 6. Oh, sorry. Half of 6 is 3. And then you square it, which is 9. And then you're going to subtract it over here. All right. So now this, 13 minus 9 is 4. this we're going to factor, and when you factor it, we have a shortcut for it. It looks like this, and you're going to take half of that number and put it there. So that's what it looks like. That's what I'm going to rewrite this as. I'm going to bring the 9 out to the front, and instead of the old denominator, I'm going to put my new denominator there, which is this. All right. I'm going to let u be equal to the part on the inside at this point. And that's just 1, so du is equal to dx, which makes us have 1 over u squared plus 4 du. And this is an arctangent problem, so I have 9. 1 over the a, which is the square root of that. Arctangent of square root of that over the a again. Don't forget your plus c. All right, 2 more things to do to simplify it there. First of all, we need to multiply the 9 by the half, so that's the first thing we need to do. The last thing we need to do is replace the u with what u equals, and that was x plus 3. And then we're good to go. There's that one. All right, so for these types of problems here, we have a polynomial on the top that has a power greater than the one on the bottom. It's probably a long division problem. So we're going to put the top one inside of the division bracket here. And when we do that, we've got to make sure that every power is accounted for. So you'll notice there's no x cubed. So I'm going to put a 0x cubed in there. We do that so that all the like terms line up while we are in the middle of the process. I'm also missing an x term, so I'll put a 0x there, and then finally a plus 5. And then the x plus 1 goes on the outside. And so basically what we do is we just ask ourselves, what do I multiply this by to get this? And we go ahead and put that on the top. So that's going to be 2x to the third. And then you multiply that times both of those and put your answer here. So that's going to be 2x to the fourth plus 2x cubed. And then we go ahead and change the signs on both of these because we're going to subtract it from above, and those go away. And then for the next one there, we have 0 minus 2x cubed, so it becomes minus 2x cubed. Bring it down, and then just repeat the entire process again. So now I ask, what do I multiply x by to get negative 2x cubed? And that would be negative 2x squared. Once again, multiplying it by both of these, we end up with negative 2x cubed minus 2x squared. And then changing the signs, these go away, and I'm left with negative x squared. What do I multiply this by to get negative x? That would be, or negative x squared, I should say. That would be negative x. So multiplying that x times both of those again, we get negative x squared minus x. Changing the signs, we get 1x. 1x plus 0x is 1x, right? And then plus 5. And then we're going to go ahead and ask us, what do I multiply x by to get x? That's a weird question, but the answer is 1. So multiplying that in, we get x plus 1. And then subtraction gives us 4 as a remainder. So now we're going to rewrite this integral as our result here. 2x cubed minus 2x squared minus x plus 1 plus our remainder, which is 4 over our divisor. Now when we do this integral, I'm going to integrate this last piece separately from the other ones here because the rule's a little bit different. Those first 4 terms are all just power rules, so that's where you add 1 to the power and divide by that value. This last one here, though, is an ln, where this is my numerator. The number in front of x is my denominator. And then we have ln of the entire denominator plus c. And of course, we want to go ahead and simplify this where we can. That's quite a long answer there. But there it is. That's the final answer there for number 30. All right, our final question here, number 31. Which integral represents the area given by b plus c? So, in other words, I want to find this area, b, added to this area, c. And that just kind of is reminding us to think about what an integral is. An integral tells you the area between a curve and the x-axis. So my function here is, we'll call it f, right? So the area under the function, between the function and the x-axis, I should say, is the integral of f of x. But from what to what? Well, if I'm doing all of b up to c, I'm starting here and I'm ending here. And that would be from 0 to 6. And so the answer is c, would be the integral that represents the area of b plus c. All right, so that'll do it for us, and hopefully that was helpful. And we'll see you guys for your test next time.